Welcome to this explainer. When we look up at the night sky, it's so easy to just think of stars as these simple, twinkling little lights scattered across the dark. But the reality? It is far more dynamic, way more violent, and honestly, far more fascinating than we could ever imagine just standing in our backyards. Today, we're analyzing the source data to really understand the entire life cycle and spectrum of stars. We're going to see exactly how these celestial bodies define the absolute limits of scale, time, and literally even physics itself. Let's get into it. Okay, let's dive right into this, because I want you to start by picturing a standard kitchen teaspoon. Got it? Now imagine taking the mass of entire mountain ranges, like entire continents, and packing it down until it fits perfectly into that tiny little spoon. What actually happens to matter when it's subjected to that kind of unimaginable pressure? Well, this is just one of the mind-bending questions we're going to answer today. It's the kind of extreme cosmic reality that sounds straight out of science fiction, but as we'll see from the data, it is a very real stage in the life of certain stars. So, to make sense of all 18 of these different celestial objects, we're going to track stellar evolution through 4 highly digestible eras. First, the realm of dwarfs. Second, giants and supergiants. Third, extreme stellar remnants. And finally, black holes and beyond. Starting things off with Era 1, the realm of dwarfs, the grounded and stable. This right here is the absolute foundation of the cosmos. We've got the orange dwarf, the yellow dwarf, the white dwarf, the blue dwarf, the brown dwarf, and the subdwarf. Grouping them like this really helps us grasp the sheer variety of stable stars out there. Now, you're likely very familiar with the mechanics of a yellow dwarf already, since our very own sun falls right into this exact category. These dwarfs are essentially the stable workhorses of the universe. They're playing the long game, quietly burning away in a perfect state of equilibrium, providing the steady light and heat necessary for solar systems to actually stabilize. They truly define the baseline of stellar existence. And this brilliantly illustrates the vast divide between those stable stars and the chaotic giants we're about to explore. I mean, the contrast here is just staggering. A red dwarf burns its fuel so incredibly slowly and efficiently that it can last for trillions of years. Trillions! To put that into perspective, our universe is roughly 13.8 billion years old. That means not a single red dwarf has ever died of old age yet. A blue supergiant, on the other hand, it burns through its fuel with such absolute ferocity that it dies in a violent flash after just a few million years, which is literally a mere blink of an eye on the cosmic timeline. Which brings us perfectly into Era 2, giants and supergiants, the chaotic and massive. Scaling up, we hit the heavyweights of the universe. We transition from blue giants and red giants straight up to blue supergiants, red supergiants, the absolute monsters known as hypergiants, and finally, the incredibly volatile Wolf-Rayet stars. These short-lived behemoths represent a massive, and I mean massive, escalation in both cosmic scale and instability. Because their cores are running out of basic fuel, these stars become severely bloated. They're basically throwing off massive amounts of stellar material into deep space by the second, fighting this constantly losing battle against their own immense gravity. They are, quite literally, ticking time bombs just waiting to collapse. And that collapse leads us right to Era 3, extreme stellar remnants, physics pushed to the absolute limit. See, when those massive giants and supergiants finally lose their battle with gravity and die, they don't just quietly disappear. No. They leave behind physics-breaking anomalies. The source material categorizes 3 highly exotic dead remnants for us here: the Neutron star, the Pulsar, and the Magnetar. These are the incredibly dense cores of dead giants that have been utterly crushed by their own collapsing weight. It creates this totally bizarre environment where the normal, everyday rules of matter just completely cease to apply. And it sets the stage for some honestly horrifying statistics. So, the crucial point here is that 6 billion ton teaspoon we talked about earlier. When a giant star collapses into a neutron star, matter is crushed so tightly that the empty space inside atoms is completely eliminated. Seriously, electrons are smashed directly into protons. The result? A single solitary teaspoon of material that weighs 6 billion tons. It's a level of density that our human brains can barely even comprehend, yet it exists in abundance right out there in the dark. But somehow it gets even more extreme when we look at the Magnetar. This is a specific type of neutron star with a magnetic field cranked up to unimaginable levels. According to the source analysis, a Magnetar's magnetic field is so intensely powerful that it could, and I quote,
Wipe every credit card on Earth from halfway to the moon. Just sit with that specific detail for a second. Over 100,000 miles away, just drifting in the cold vacuum of space, this stellar remnant possesses enough invisible magnetic force to instantly erase global data systems on our planet. It perfectly highlights the absolute terrifying power of these dead stars.
Let's move to and see how this builds into our fourth and final era, black holes and beyond, the ultimate collapse. We've seen matter compressed into unimaginable density and magnetic fields capable of crazy long-distance destruction. But what happens when a dying star is so incredibly massive that not even the dense core of a neutron star can stop the collapse? Well, this ultimate structural failure leaves us with two potential end states: the infamous black hole and the highly elusive quark star. Both of these represent the absolute final victory of gravity over everything else in the universe. Now, what's really interesting about this concept is that it brings us to the very edge of human understanding. A quark star is defined as a hypothetical star that might exist directly between a neutron star and total collapse into a black hole. We're talking about a concept so elusive, it pushes the absolute boundaries of known physics. The idea here is that gravity becomes so incredibly intense that even the neutrons themselves are crushed, dissolving into a massive, pressurized ocean of their fundamental subatomic building blocks, known as quarks. It's a transitional state of matter so extreme, astrophysics is still actively searching the skies for definitive proof that they even exist.
And that leaves us staring directly into the cosmic abyss with one final, deeply provocative thought. What is the ultimate fate of matter falling into a black hole or a quark star? I mean, if stars can crush matter into a 6 billion-ton teaspoon or melt it down into a subatomic quark soup, what happens when it crosses the threshold of a black hole where no light escapes and physics breaks down entirely? The source data gives us an incredible map of stellar evolution, but the universe always leaves us with one more mystery. Thank you for joining me on this explainer, and never stop looking up and questioning the brilliant, terrifying, and completely extreme universe we live in.